Great.
Hello, everybody. I'm Lars Lindemann and currently a postdoc at Penn. And today I'm going to talk about our recent work on temporal robustness of stochastic signals, which is joint work together with Alina Rodionova and George Papas, who are also at Penn. In this talk, we focus on time-critical systems, so systems in which meeting stringent real-time constraints is of major importance. In fact, many cyber-physical systems are time-critical, and I've shown here some examples of time-critical systems such as air traffic control systems, but also autonomous driving systems, train scheduling, and automated warehouses. I especially want to note that connected and multi-agent systems are often time-critical. And importantly, in many of these systems, failing to meet real-time constraints can really jeopardize the safety of the system. So the first question is, of course, what are the reasons for failing to meet such real-time constraints? Well, there may in fact be various sources of timing uncertainties that can lead to such failures. In network control systems, there may be delays in communication, computation, actuation, or even in sensing. For instance, in scheduling algorithms on embedded hardware, there may be delays in the computation. But also connected systems such as self-driving cars can be subject to timing uncertainties. In fact, Elon Musk stated recently in an interview that if you have a stack up of timing tolerances, then you can have a variable latency, which is called jitter, and which can make it hard to anticipate how to turn and accelerate the car. So in summary, robustness against timing uncertainties is critical. And we were asking the question in this work, how can we analyze temporal robustness? We claim two main contributions in this work. First, we define a notion of asynchronous temporal robustness for real-valued signals that we deem particularly useful. Second, we define temporal robustness for stochastic signals using notions of risk. Of course, there has been previous research on this topic that I now want to briefly summarize. There has been research on spatial robustness. However, spatial robustness does not necessarily correlate with notions of temporal robustness. More with respect to temporal robustness, there have been task scheduling algorithms, there has been research on robust timed automata, on hybrid systems conformance, and on temporal robustness for temporal logics. However, these works mostly consider temporal robustness only over abstracted domains. And there is in general no consideration of asynchronous events, and there's no notion of risk for stochastic signals. Okay, let us now introduce temporal robustness on an example. Therefore, assume we're given a signal X that consists of two subsignals X1 in red and X2 in blue. And we want that this signal satisfies a specification. In fact, we want that the difference between the first and the second subsignal is below 1 within the time interval of 145 and 155 seconds, which is indicated here in green. To express this specification, we define the function h, which is shown as a black signal in the plot here. And we naturally see the specification is satisfied if the signal is non-negative for all times in our time interval. We also define the satisfaction function beta, which evaluates to 1 if the specification is satisfied, as said before, and it evaluates to -1 if the specification is violated. So if there's one time point here for the black curve that is below 0 in the time interval. For this example, we're now asking the question, how should we define temporal robustness? In the paper, we present two notions of temporal robustness. The first one is the synchronous temporal robustness. The idea here is to shift the signal X synchronously in time until the specification is violated. So here on the left, you see our original setup. And now we're shifting the signal X by 5 time units to the right, as you can see here in this figure. And the specification is still satisfied. So let's shift a little more. Let's shift by 12 time units. And we see that still the signal satisfies the specification. So let's shift again a little more. However, now if we shift by 13 time units, as shown in the right plot, we see that we violate the specification because there's one time point that is negative in our interval. So in fact, in this case, the synchronous temporal robustness is 12, which means that we can shift the signal by 12 time units to the left and to the right without violating the specification. We can even put this in math, and we define the synchronous temporal robustness eta to be equivalent to the maximum time shift we can find where we still have the same satisfaction of the shifted signal with a non-shifted signal. In the paper, we also define the asynchronous temporal robustness. The idea here is to shift the subsignals x1 and x2 individually in time. So we're shifting them asynchronously until the specification is violated. So for our original setup, let us now shift the first subsignal by 1 time unit to the right and the second subsignal by 1 time unit to the left. And we see here that the specification is still satisfied. So let's shift a little more. Let's shift individually by 3 to the right and 2 to the left. And we still see the specification is satisfied. However, if we now shift a little more by 4 and 3, we see that the specification is violated because here the black signal drops below 0. So it turns out in this case that the asynchronous temporal robustness is 3, meaning we can shift each subsignal by at most 3 time units while still satisfying the specification. We can again put this in math, and we define the asynchronous temporal robustness theta to be equivalent to the maximum individual time shift such that we have the same satisfaction property. As a direct consequence of these definitions, the temporal robustness quantifies the permissible timing uncertainty. In fact, the synchronous robustness upper bounds the permissible synchronous time shift such that the satisfaction of the shifted signal and the non-shifted signal is the same. The same holds for the asynchronous temporal robustness that upper bounds the permissible asynchronous time shift such that the satisfaction of the shifted and the non-shifted signal are the same. We also show the computational complexity in the paper, assume that we have a maximal desired robustness R, then calculating the synchronous temporal robustness is polynomial in R. However, the asynchronous temporal robustness to calculate it is exponentially in n, which is the dimension of the signal. We also show in the paper that the synchronous robustness naturally upper bounds the asynchronous temporal robustness. Okay, so let's look at a case study in which 3 cars have to pass a T intersection. The specification is a Boolean specification that requires that whenever the green car is in the middle of the intersection, the distance to the red car and the distance to the blue car has to be at least 15 meters. Okay, so what you're going to see here is in the left side, the scenario in which no car has any delays. On the right-hand side, you can see the green car having a delay of 12 seconds and the red car starting 12 seconds too early. In the nominal scenario, you see that the safety constraint is satisfied at all times, while you see here in the shifted scenario where the cars have delays, that the safety constraint is violated, which you can also see here by the green and the red cars being closed. Okay, so in this case, the asynchronous temporal robustness is 11. Let us also look at the second case study that is formulated using signal temporal logic. So our temporal robustness notions also translate to temporal logic specifications. The task description here informally given is that we're having 2 robots and both robots should recharge here in the charging region, eventually gather together in region B and periodically visit region A. And the satisfaction of all of these subtasks is shown here. And you can basically infer that when the lines are green, the specification is satisfied. So here, the second robot charges, then the first robot charges, regions A are periodically visited. And here you will see in the other subfigure that robots 1 and 2 are in region B at the same time. So the specification is satisfied. The synchronous temporal robustness is 7. So if we shift both robots by 8 time units, we see that we violate the specification. In fact, robot 2 is not sufficiently long in the charging region given over there. The asynchronous temporal robustness is calculated to be 6. And if we shift robot 1 by 6 and robot 2 by 7 time units, we see that the specification that both robots being simultaneously in region B is violated. So robot 1 basically is now approaching region B, but will leave region B when robot 2 reaches it. And by that, the specification is simply violated. So here you can see this point. Okay, so far we have dealt with temporal robustness over deterministic signals. However, once we employ systems in the real world, uncertainties will inevitably render systems to be stochastic. For instance, in the case of our car example here, the velocity of the cars may be subject to noise so that the trajectories of the cars are drawn from or described by a distribution. In fact, the temporal robustness then also becomes a distribution because each noise realization will lead to a different trajectory that leads to a different temporal robustness value. And the question that we were asking ourselves is, how can we define temporal robustness for stochastic signals? And can we measure the risk of not being temporally robust? And in order to answer these questions, we use risk measures, and risk measures can measure risk over a cost distribution. For instance, assume we have a cost distribution here indicated in blue, then a common risk measure is the expected value or also the worst case. However, in this work, we specifically want to focus on tail risk measures such as the value at risk or the conditional value at risk. I'm not going to provide any formal definition here, but the value at risk at level beta, for instance, is the 1 minus beta quantile. So why not use the expected value simply? Well, the expected value may give us good performance, but is not necessarily safe. And if we're interested in safety, why not use the worst case? Well, because then the streets may simply be empty because no car is driving, right? So we believe that tail risk measures are good in the sense that they trade off average and worst case cost. So how do we use these risk measures now? We define the synchronous temporal robustness risk by picking any risk measure, for instance, the value at risk, and wrapping it around the negative synchronous temporal robustness. Why do we pick the negative synchronous temporal robustness? Well, basically because risk measures are defined over a cost distribution, and in this case, the negative synchronous robustness is our cost. Similarly, we can define the asynchronous temporal robustness risk by just picking a risk measure and wrapping it around the negative asynchronous temporal robustness. So the next natural question is, of course, can we compute the temporal robustness risk? And the answer in general is no, we cannot do that. However, we can estimate the temporal robustness risk from data. And we're going to show this now for the value at risk, but I want to emphasize we can do this for any other risk measure as well. So assume we want to estimate the asynchronous temporal robustness risk. So Z is set here in this case to the negative asynchronous temporal robustness. And assume that we have observed n trajectories that lead to n different temporal robustness values that we consider here to be ordered already in an increasing way. So the ith temporal robustness value that we have observed is not greater than the I+1th value. Then we obtain upper and lower bound as follows. The upper bound is basically the n times beta plus gamma highest value that we observe. And the lower bound is the n times beta minus gamma lowest value. And gamma here is a constant that is given as follows, where delta is a failure probability that we're willing to accept. And then we show that with a confidence of 1 minus delta, it holds that we have in fact obtained upper and lower bounds. Okay, let's look again at the t-intersection scenario. In this case, however, we assume that the initial times of the cars are uniformly distributed within minus d and d, where d is the maximum permissible delay. What we did then is we varied this maximum permissible delay here in the rows, and we calculate risk measures, so the value at risk at different risk levels. So here at the 5% quantile upper and lower bounds, and at the 2% quantile upper and lower bounds. The first thing we observe is that the estimates are tight. So if we look in the first and second column, the values are very tight. The second thing we note is that the estimates tell us how much more timing uncertainty we can sustain. In fact, in the paper, we show that the risk, if the risk measure is monotone and translationally invariant, which applies to most of the risk measures, then the risk of the perturbed system is upper bounded by the risk of the non-perturbed system plus the maximum permissible delay. We can see this here. If we don't have any delay, our risk is minus 10. And that tells us by this bound that our risk for a maximum permissible delay of 10 is at most 0, which holds, which we have verified here. I also want to show the following case study. On the left side, you see the t-intersection that we looked at before. And on the right side, you see the same intersection, but the velocities of the red and the blue cars are now flipped. We see something very interesting if we look at different risk measures at different risk levels. Basically, at the 15% quantile, the risk measures tell us that the scenario 1 on the left-hand side is the least risky one, while risk measures at the 5 or 2% quantile tell us that the scenario 2 with the flip velocities is the least risky one. And this is also what we can see here in the plot of the distributions, where the blue distribution has a tail of very non-robust realizations. And by that, I'd like to thank you for your attention. Also, we have code online that you may want to have a look at, and I'm happy to answer any questions now.